Welcome back. So in this last problem in this section, we will actually define a region that we will revolve around an axis and find the volume that is generated by this revolution. And we'll be using both the disk and the shell method. So what region are we looking at here? It is bounded by 1 over x, y equals x, and y equals 2. So what is that region? Well, 1 over x, my rational function, y equals x, the bisector of the first quadrant, and y equals 2, my horizontal line. So this is the region right here, bounded by all three curves. It's not very hard to find the point of intersection, so we will leave this as an exercise. They're given here in the diagram. The important one here, they're all important, but the one that actually matters perhaps the most is 1, 1, this point of intersection right here. So let us actually start by using the disk method. So how do we position the little rectangle when we use the disk method? Well, it's got to be vertical because when we use the disk method, we are always positioning the rectangle so that it is perpendicular to the axis of rotation. This symbol means perpendicular, as you know. Okay. What is the first thing that we notice when we do this? Well, this region here, the y high and the y low are 2 and 1 over x. The y low is on the rational function, but here, on this side, the y high is still the same, y is equal to 2, but the y low is actually on the line y equals x. So different y lows means different regions. We're going to have here to split the region in two at the point of intersection where x is equal to 1. The next thing that we notice is that neither rectangles are actually connecting with the axis of rotation. So another bother, we're going to have to extend that rectangle, both of them actually, all the way down to the axis of rotation, creating, as we know, a big R and a small r. So let's take a look at the first part, the one that is on the left of x is equal to 1. What's the big R? Well, it's y high minus y low. So the big R is 2 minus 0, so it's 2. Little r, for the first region, goes from the rational function to the axis of rotation. That rational function is 1 over x, so 1 over x minus 0, giving us the following volume. Integral of pi big R squared minus little r squared, that's our formula. And the integral goes from, well, the point here, if you remember, was 1/2, and this is 1. So these are the bounds of my integral. Big R squared, 2 squared, little r squared, 1 over x squared. We'll come back to this in one moment. Now let's take a look at what happens on the right side of the axis x is equal to 1. Big R, again, y high minus y low, so big R is 2. Y high is 2, y low is 0. So 2 minus 0 is my big R. My little r, y high minus y low, the y high is on the line, so that's y is equal to x. Minus 0, we get x. So v2 is actually the integral of pi big R squared minus little r squared. This time, this runs from 1 to that point, which if you remember was 2, 2. So the integral 1 to 2, pi is outside, 2 squared minus x squared, giving us the following volume. We add the 2, v1 plus v2, so the integral from 1/2 to 1 of pi, 2 squared is 4, 1 over x squared is 1 over x squared, plus 1 to 2, so 2 squared is 4, and x all squared is x squared itself. So let's finish this calculation over here. What is it that we get? Well, the integral of 4 dx is 4x, and the integral of minus 1 over x squared dx is just positive 1 over x. On the other side, the integral of 4 is 4x, and the integral of x squared is x3 over 3. Applying the bounds according to FTC Part 2, a result we know well. Upper bound 1 and 1/2. Here, upper bound 2, lower bound 1. We end up getting in this bracket 1 and in that bracket 5/3. And when we add those two, we get 8 over 3 pi cubic units. Okay, that was some work. Now, let's see if we can actually do this problem again using the cylindrical shell method. Well, cylindrical shell requires the rectangle be positioned parallel to the axis of rotation. So we've positioned the rectangle here because my axis of rotation is the x-axis. Notice that we do not need to break the region into two parts because the x-right and the x-left are exactly the same wherever you put the rectangle throughout. Okay, so in this little part of the course, we have learned that big R is the radius, and it's also the distance from the rectangle to the axis of rotation. That's big R right here, distance from the rectangle to the axis of rotation. As for the height, h is the length of the rectangle, which in this case will be x right minus x left. So let's identify those quantities. Since big R is basically the distance from the y-axis to the rectangle, this is a displacement along the y-axis. We don't really know how high it is because the rectangle could move up, it could move lower. So what do we call a distance that is parallel to the y-axis? We call it simply y. The height is, because it's horizontal, x right, x left, so we have to isolate the x right here. Basically, x is equal y, so it gives itself away. As for the x left, over there, we have to isolate the x from y is equal to 1 over x. So cross multiplying, we get 1 over y, which will give us a formula for cylindrical shells is the integral of 2 pi rh. Going to replace big R with y and h with y minus 1 over y. Notice here that the bounds are actually bounds in y, so they will go from y equals 1 to y equals 2. These are the bounds for this integral. So all we got to do is solve this, which looks a little simpler than the one using discs. So let's multiply it out. Y times y is y squared. Y times 1 over y is just 1. So the integral of y squared is y3 over 3. The integral of 1 dy is y. Pull the 2 pi outside. My bounds are 1 and 2. So FTC part 2, plug in the upper bound 2, 8/3 minus 2. Plug in the lower bound 1, minus 1/3 plus 1. So basically we get 4/3 inside of this bracket times the 2 pi that we have outside gives us, of course, the same answer as the one we got using discs, so 8 over 3 pi cubic units. As a conclusion, all we can say is that, yes, indeed, the shell method looks to be a little faster and more efficient in order to reach the answer. And that concludes that little video. I'll see you in the next chapter, which is arc length. Goodbye.